Welcome to this introduction to HDL design in SystemVerilog. We'll build the foundation you need before writing any real hardware code. So where are we heading? We'll start by answering a fundamental question. What exactly is an HDL or hardware description language? And just as important, how is an HDL different from traditional software? Next, we'll walk through the major steps of a design flow. After that, we'll explore the three fundamental digital design styles: Dataflow style, behavioral style, and structural style, and we'll demonstrate them using a multiplexer. By the end of this introduction, you'll understand how hardware designers think, how digital logic is described in SystemVerilog, and how a design moves from concept to working hardware. An HDL, or hardware description language, is a specialized computer language such as Verilog, SystemVerilog, or VHDL. It is used to describe the structure and behavior of electronic circuits. The result of an HDL description is a hardware, synthesized logic on an FPGA or an ASIC, not a program running on a CPU. In practice, an HDL describes something physical. You are specifying wires, gates, and registers that all operate in parallel. And because this is real hardware, time matters. The behavior depends on electrical signals that take time to travel. A good analogy is stage design versus a script. With an HDL, you specify the stage, the lights, the props, and the wiring. When the curtain rises, everything happens in parallel. The lights change, the doors open, and the music starts. Software, on the other hand, is like the script. First say this, then move there, then play the music. It is a sequence of commands happening one after another. And on the same stage setup, you can run many different scripts. Let's walk through the major steps of the digital design flow. We begin with high-level design, or architecture. At this stage, block diagrams and waveforms are used to capture the overall system behavior and data flow. Next comes RTL design, written in languages such as Verilog or SystemVerilog. Here, the functionality is described cycle by cycle in terms of registers and logic. After that is verification, where we check if the logic is working correctly. Verification is an iterative process that runs side by side with RTL design. You refine the RTL, run simulations, find bugs, fix them, and repeat until the design meets the specification. The next stage is synthesis, where the RTL is translated into a gate-level netlist. For an FPGA, this produces a configuration file that maps the logic into the device. Then comes physical design, where the gate-level logic is turned into physical masks. These masks define how the transistors and interconnects will be laid out on silicon. Finally, fabrication uses those masks to manufacture the chip itself. It is important to note that stages 1 through 4 are relevant to both FPGA and ASIC. Stages 5 and 6, physical design and fabrication, are relevant only to ASIC. If you found this content valuable so far, consider supporting the channel by subscribing. It really helps the channel grow. Let's design a 2-to-1 multiplexer using the Dataflow style. Dataflow style describes a circuit by directly expressing the flow of data between signals. We have our equation, the truth table, and a small chart of bitwise operators that we will explain later in the course. For now, we use them like logic gates, not AND and OR. First, we write module mix2 and end module. At this point, we have an empty box named mux2. Next, we add the inputs and the output to the code, and label them on the black box as well. Inputs A and B are the data lines, S is the select, and Q is the output. Now we add the data flow code with an assign statement that mirrors the logic inside the box. Q is assigned S complement and A or S and B. This is exactly the gate diagram written as a single expression. Finally, we can implement the same design using the ternary operator. If S is 0, Q equals A. Otherwise, Q equals B. Both versions synthesize to the same 2-to-1 multiplexer. Let's design a 4-to-1 multiplexer using the Dataflow style. We have the behavioral equation, and the truth table that shows the select lines S1 and S0 choose exactly one of X0, X1, X2, or X3 to pass to Q. Now let's map that equation to logic gates and continuous assignments. In Dataflow style, we use the assign statement with simple logic operators, not, and or. So Q is assigned directly based on the expression of the select signals and inputs. We can also describe the same multiplexer more compactly using the ternary operator. If S1 equals 0, then the answer will be X0 or X1 depending on S0 value. And if S1 equals 1, then the answer will be X2 or X3 depending on S0 value. Let's design a 2-to-1 multiplexer behavioral style. Behavioral style refers to writing code that describes what the circuit should do rather than how it is built. The truth table shows that when select S is 0, Q equals A, and when S is 1, Q equals B. Let's look at an implementation using always combinational. We will use an if-else statement. If S equals 1, then Q takes the value of B, else Q takes the value of A. Finally, we can also write it using a case statement. Case on S. When 0, Q equals A. When 1, Q equals B. The result is the same 2-to-1 multiplexer, just expressed in a different coding style. Now let's design a 4-to-1 multiplexer. The chart shows that the select inputs S1 and S0 choose which of the 4 data inputs is passed to the output Q. We will implement the design using an if-else structure. Here we use logical operators. Logical not, written as exclamation mark, logical and, written as double ampersand. Logical operators return only true or false. Using these operators, we can check the value of the select lines and assign Q accordingly. Finally, we can also implement the 4-to-1 multiplexer using a case statement. Case on the select inputs S1 and S0. For example, when 0, 0, assign Q equals X0, and when 0, 1, assign Q equals X1. This gives us the same 4-to-1 multiplexer in a clean, structured coding style. Here we see the equation for a 4-to-1 multiplexer. To make the design easier to manage, we will break the logic into smaller building blocks. As we have seen, the full equation can look long and messy. A good practice is to reuse existing modules. So in this design, we will build the 4-to-1 multiplexer using our 2-to-1 multiplexer blocks, following a high-level architecture. First, let's define the inputs and outputs. The data inputs are X0, X1, X2, and X3. The select signals are S1 and S0, and the output is Q. Inside the design, we will create 2 internal wires called N1 and N2. Next, we make 2 instances of the 2-to-1 multiplexer, which we call M0 and M1. When connecting to ports, we can either rely on the order of the inputs or use named port mapping like .A, .B, and so on. The professional way is to use named ports, such as .A X0, because it makes the code easier to read and reduces mistakes. Now we connect the inputs and outputs according to our architecture. M0 selects between X0 and X1, producing N1. M1 selects between X2 and X3, producing N2. Finally, we add the last multiplexer, called M2. M2 selects between N1 and N2, using S1 as the control, and its output drives Q. Now that you've gained a solid introduction to the world of hardware design and understand how digital circuits are planned and built, it's time to look at the other half of the development process. To truly ensure that the hardware we create works correctly, we need a structured verification methodology. So I invite you to watch the next video, where I explain UVM, Universal Verification Methodology, and walk you through the process we use to verify digital designs. If you'd like to dive even deeper, you can explore my full course, which is linked in the description of this video. It's a great next step if you want to expand your skills and continue developing as a hardware or verification engineer.